Welcome to the E6S Methods podcast with Jacob and Aaron, your weekly dose of tips and tricks to achieve excellent performance in your business and career. Join us as we explore deeper into the practical worlds of Lean, Six Sigma, project management, and design thinking. In this episode number 209, we introduce various types of statistical process control charts in Process Pulse Part 1. If you're just tuning in for the first time, find all our back episodes on our podcast table of contents at e6s-methods.com. If you like this episode, be sure to click the like link in the show notes. It's easy. Just tap our logo, click, and you're done. Tap, click, done. Here we go. Hey, Jacob. How are you?
I'm great, Aaron. How are you doing?
Jacob, I am doing delightful.
Excellent. It's a new word.
Or is it delightfully? I don't know.
No, I'm keeping delightfully.
I'm doing well, thank you.
Excellent.
And so, good that we're going to get back into the swing of things. And I thought I'd turn up the heat a little bit with some of the more technical tools that I'd say for the last year or so we've kind of skirted around. So I think it's time to get back to our roots a little bit.
Excellent.
So this one is going to be on statistical process control, or SPC. And I'm likening it to the process pulse. If I think about statistical process control, I think about monitoring the most important vital signs of a process. And to me, it's just like monitoring your pulse and just looking for anything that goes a little bit haywire.
All right. Let's see what we have to talk about it.
We got lots.
I know.
So getting back to some of our old ways, let's talk a little bit about what some of the objections might be to somebody saying, hey, we don't need statistical process control. We don't have the time to look at and analyze every single data point. What do you think about that?
I mean, that's true. Just kidding. I mean, the idea is you don't necessarily need to look and analyze critically every data point. The chart, be it depending on what sort of chart you decide, will, by just plotting it on that chart, it will show you what are some of the areas or things that you should start getting concerned about. Is it trending in a direction where you need to be worried about? Is it actually behaving in the way you expect it to behave? Those things become much more simpler or easier to identify visually when you plot them on a control chart.
Yeah, and I mean, this doesn't take into account that there are sampling plans that come along with this. Not all processes are you doing 100% sampling. Most processes you're not, as a matter of fact.
Or you shouldn't.
Right, yeah. But you do want some sort of representative time sample that would give you an indication if things are, well, steady, I'll say.
Yep.
And how about this? We already do SPC, but it really isn't helping us with anything.
I've heard that a lot, and I think my point is, are you doing it the right way? But with the question being, are you doing it just to show people that you're doing something about it? Or do you have an engineer or do you have somebody who's knowledgeable enough to look at that chart and to be able to tell you, here's what you're seeing or here's what you're looking for? And then the most important question comes, are your limits or things that you're checking yourself against, are they actually what it should be, or is it different? That's at least my experience been with it. And, sometimes in certain cases, your process is so damn strong or so really good that SPC is actually just telling you that don't worry about it. It is working as it's expected to. Just keep going.
Yeah, I guess somebody might consider that to be not helping. But for me, even if it wasn't giving any signals, I don't know if I'd consider that to be a
negative.
Yeah, right. It's the absence of a problem is not necessarily a negative, I guess, in that manner. But that doesn't make it useless, I should say.
Correct.
So, yeah, and really get it. This whole real time thing. I gotta say, I've actually seen very few companies actually do it properly, real time, using the right folks to really interrogate the process and monitor it. Usually, it's say, oh, the month is over, customers coming, we need to show our SPC charts, so let's put them together, engineers, and then if you had any signals, you can't actually answer for what'd you guys do during this time. You're like, I don't know.
Exactly. I mean, ideally, these are sort of, and again, shouldn't speak common to everything, but a lot of the packages or software or tools that most organizations have, I am hoping against hope that these controls are put in the background. So when you are recording certain data, it is checking against these and kind of validating is it in the line or not, because there, a lot of poka-yoke, if you want to call it, in some of the instruments or machinery, it kind of exists in the background, or it should exist in the background.
Mm-hmm.
I forget what we're using in our chemical world, the software for QC. I forget what, WinLims or something. WinLims,
Mm-hmm.
yeah. I mean, in the background, I know it had the statistics. So if you're plotting this, or if you're actually even recording the data, it kind of makes you or gives you a warning to say, is this really what you entered? Because it doesn't look like it should be what it should be.
Right. In that case, it was dynamically checking everything either against some set limits based off of a previous history, right? Yeah. Or I don't know. Yeah, I think we always did set limits. I don't think we really had dynamic limits in that. But some software, like Minitab, you can choose either or to be dynamic or set.
Exactly.
All right, just a little note here that there's a lot of images in this. So anybody who's listening along, they might want to check out the website and hit the link and take a look at the show notes to look at some of these images. All right, statistical process control history. Walter. I don't know where Robert came from.
Yeah, I don't know where he came from.
Walter Schuart, who worked for Bell Labs in the 1920s. And what always strikes me about just looking at the history of any of these things, what we're looking at here is roughly 100 years later. And in some industries, we're still talking about it as if it's novel and brand new and won't work.
Yeah, exactly.
It kind of drives me crazy, but that's just the way things work, I suppose. The basic, we've already shown statistical process control in the past, and let's see, it looks like that's episode 64 and 65, stable and capable. Just looking at the anatomy, it is just looks like a line drawing with a bunch of connected dots, and it's plotted over a series. X-axis is the time axis, the y-axis is whatever your metric is. There's a center line in the middle that represents the mean of all the measurements, and then there's upper and lower control limits, which are based off of roughly 3 standard deviations. And one of the key rules, the one main key rule everybody uses, is if a single point goes outside of either the upper or lower control limit, then you may have a special cause variation, and that you might want to check it out. That would be your abnormal situation.
Correct.
All right, so I got a little example here.
Okay.
Oh wait, actually, let's right here. Another note. So I said it monitors the health of the process. So you already mentioned it's looking at trends, right? Mm-hmm. Abnormal changes and variations. Say if you have a really tight process and then all of a sudden it starts to swing back and forth pretty widely, it'll pick up on that. And also major shifts from I said target, but I really mean from the center line. So if you had like a step change over time, it would pick up on some of those things. So there are some rules to help pick up on that.
And we'll cover all the rules in detail later, I'm sure.
Yes.
Got
an example here, and it's actually a real one.
Ooh.
So let's see. An operator on a ceramics coating process monitors the coating weights applied to each part. The process flags for Rule 1 violation for statistically lighter than usual coating weight. And I've kind of outlined here what the proper action would be. Can you walk us through that?
Sure. It's like that and-on chords sort of a situation when something's not necessarily in the limits what you want to. You stop everything. You then swarm. You inspect the part. Confirm is it still within the specification of what your customer would accept. While you're doing that, get an understanding of what is causing this to happen. Did we change something? Did something else happen? What is impacting this process that's resulting in your part being lighter than the usual, what you're expecting? And if it's good, nothing's changed, somewhere capture the note that what you did, why you did, and why you made the decision to continue as it is. Or if it is really significant and something's not working the way it should, then, get help. Notify the others and fix the problem before you start the process back up again.
Right, and that's his. It is kind of an ideal world, though, right?
Exactly.
So, what would you say would be more typical of what you'd find?
Typical would be you would let the supervisor know, but you would keep still the line running and pray to God that the next part is not coming the way it is. And probably when you see 2 or 3 parts that way, then you probably considered escalating it and doing something about it.
Yeah, that sounds about right. So there is an image that shows what it looks like to have a couple parts that fall underweight for this ceramic coating process.
Yeah.
And everything really does matter on. You have to pick the right metrics. That's one key thing is a lot of our companies, it is good, in my opinion, to look at most metrics in this manner, except that most of our companies have far too many metrics. And looking at too many metrics in this way is a little bit fatiguing. Leadership looks at them and they're like, I don't know what those mean, and don't bother me with that much detail. Just give me a number, kind of thing. So that's standing in the way of this. So use the tool more where it's going to be most accepted, and it's generally among those that are technical and very familiar with the process in which they're measuring.
That's true. And even to your point, even the SPC, there are different versions on what you should use when and where. And even that also can be tricky.
Absolutely. Well, that's a good segue. So how about you walk us through some of those basic types?
You are listening to E6S Methods Podcast, brought to you by E6S Industries. Join us on our website at www.e6s-methods.com. Journey through success.
Are you applying for professional certification in your field? You'll be happy to learn that all this time you've been streaming Jacob and me into your ears, you've also been earning continuing education units, or CEUs, which can be applied toward most professional certifications. You can do your research, all the math, and figure out which episodes are applicable for which discipline, or you can save yourself the time and hassle and just order a CEU report from us. All you need to do is provide us with which episodes you've listened to, and we'll provide you with a portfolio including details about each episode and a certificate of recognition with a CEU breakdown by competency, including leadership, tactics and tools, strategy deployment, and principles and philosophies. So if you have certification on the mind, start here and save some time. Just go to e6s-methods.com/CEU to order yours.
Oof, now this is the hard part. I haven't used many of these for a long time, so you're putting me to test. But I think the simplest and the first chart that we've shown, which resembles a SPC chart, is what is known as a IMR chart, or the individual moving range chart. And this is mainly used when you have some sort of a continuous data. When we say continuous data, for those who remember, it's basically numerical data that has decimal points or something that accompany it. And the data is not something that you're subgrouping or sampling, if you want to call it. It's basically, for the most case, every part or every individual piece is being measured, is kind of how I would differentiate. And I don't know if you would call subgrouping something different.
Well, I guess it's a single thing. So you could say it could be a sample, like a one piece taken from a batch, if you wanted to look at it that way. Yep. But you're not taking the average of multiple samples in that case.
Correct. The second, or probably the more common one that you would see, is what is known as an X-bar R chart. X-bar, as it stands for, is mean, for those who remember their statistics. And R is, again, the range, which basically, again, it is for continuous data, but you're using X-bar, which is basically an average of a few parts that you're doing. So there's some level of grouping or subgrouping that's going on when you're measuring that individual data point on that graph. So these X-bar IR and the IMR chart are probably the more common ones that you would see for continuous data. When you're looking at more discrete or attribute data, you're looking at two main kinds. One is a proportions chart, or known as a P chart, or the other is known as a U chart. Again, both of them have subgrouping kind of built into it. One is looking more at proportions or percentage. That's the P chart. And the U chart is more looking at a DPU, which is defects per unit, or opportunity, DPMO option. That's what they're looking at more.
Right.
So, and for me personally, when I had to do this, until I started doing something, which was again very rare, differentiating when do I use a percentage versus when do I use a DPMO was hard. So Aaron might have a much better example on how exactly to do that.
Yeah, well, so for the proportion, so let me just stay for I'd say 90% of anything you might need to measure. You could use an IMR, X-bar R, or a P chart.
Yeah.
If you are in a situation where you really want to know, get a decent review of defects. So proportions is more for defectives, and that nuance is a little bit different. So this is the count of defective parts versus the count of total parts, and that can give you the proportion defective. U is if you are looking for defects where there are multiple possible on a single unit. And basically, they'll all get averaged out with the number of units that you're actually looking at. So you could have, say, for instance, 3.115 defects per unit. So on average, every unit roughly would have, at least 3 defects, and you have some decimal places. It's kind of counterintuitive. It doesn't really make sense until you really get in there and start to work with it as a chart. I'd say for most people see it in the classroom for the first time, it doesn't quite resonate. So, but I'd say with these 3, IMR, XBAR, R, P, plus the U, you really take care of, I'd say, 99.9% of any control charts you might need to do.
Correct. And if you're going beyond that, that means either you have a very complicated process or you as an individual are complicating your process.
And with that, we say, but wait, there's more.
So Aaron, what are the complex ones that you have encountered or you have used a little bit here and there?
Well, I won't claim to have used very many of these, certainly not in a application outside of the classroom, but I just want to introduce some of what are available. So there's also one called XBAR S, and it's a little bit of a variation from the XBAR R. It's still mean, but it's no longer using range anymore. It's using standard deviation. Yep. And it's still the same, rational subgrouping continuous data, but when you're dealing with large sample sizes, it is actually better to estimate standard deviation variation in the process for your control limits with actual standard deviation and rather than range. So, and this is this comes up mostly because now we have a lot more availability of data. It's easier to take samples and it's much easier to crunch the data.
Correct.
Where XBAR R was invented, everything was done by hand. So small samples and just a little bit of simple math were used to estimate everything we needed. So then we have NP, which is a lot like the P for proportions. But this one actually, instead of creating it and turning it into a percentage, we're actually just doing the counts of defective units. So if there was 3 out of 100 defective units, we wouldn't say 3% anymore. We would just say there's just 3 defectives, and it would only plot the raw discrete number count. Similar, the C plots individual counts of defects as opposed to defective units. So it could be a little bit like the U chart, except we're not doing defects per unit. We're just counting the number of total defects. And there's the little nuance there. Personally, I'm not interested in NP and C, the counts. I'd rather see it normalized based off of the subgroup size. So,
or I'm happy using a percentage.
Yeah, exactly. So then there is the ZMR, or as some people might call it, the short run chart. And every plot is converted into this Z-score. And yeah, I don't know if we've ever talked. Have we talked about Z-score yet?
Maybe we had to in the beginning.
We are gotten far enough where I'm actually forgetting what we've talked about, what we haven't.
That's true.
So I'll have to check the archives, or maybe somebody who's gone all the way through the catalog can come back and say, "Hey, Aaron and Jacob, no, you didn't. What's the Z-score?" But we'll talk about it a little bit here. We're still looking at continuous data, no subgroups. We are looking at, so everything is converted into Z-score, and this is essentially units of standard deviation, so units of sigma. So where is this fall between negative 3 sigma and positive 3 sigma relative to the variation? It's confusing. We're not going to be able to teach you the Z-score here, but basically this is the only one that's really useful if you have low volume production and you have a high mix of different parts. So you've got a lot of different parts all running on the same machine. This helps you compare sort of apples and oranges. You can use the data from all types of parts that you're running on the same equipment to give you an indication on if that equipment is running properly. So say if you're only making 10 parts of one widget and 10 parts of another widget and 3 parts of a third widget, you could use all that data together in this normalized Z-score world and see if your process itself is behaving differently.
And I think that's a key part here, right? You got to be careful when you use this, because it's not necessarily anything that you're doing about the part anymore. It's about the process or about the equipment. That is what is giving you the information on, and you have to be conscious and careful about that.
Absolutely. And it does rely on a bit of an assumption that variation in all types of parts is going to be similar.
Consistent, yeah.
Yeah,
Exactly.
consistent, yeah. So it does take a little bit, but I have found that in a lot of small companies, when they try to run statistical process control, they're always like, well, we want to, but we never get enough data to have it make a difference. By the time they run their setup and run their parts, it doesn't really matter what's going on.
Mm-hmm.
They're just running off large batches. And then there is the Laney P and the Laney U.
I don't even think I've heard about them.
Yeah, this one came about when I moved into the telecom industry. Because of the large amounts of data, you can have an artifact of large sample size. Again, getting back to all these things were used to be done by hand. So for the P chart and the U chart, the control limits are decided by sample size, like sample size is in the denominator. So the distance between the control limits artificially shrinks when you have hundreds to 1,000 in pieces in the sample size. So this is, Minitab now has a little alarm in there that says, hey, you got too much of a sample size. You need to use the Laney instead of these other ones, because you're going to artificially shrink your control limits and everything is going to look out of control. We call that over dispersion.
Okay, makes sense.
Coincidentally, when you have a sample size that large, if you don't have a Laney P or Laney U at your disposal, you can get pretty much the same practical information just by plotting it on a IMR chart. It roughly works out the same. So somewhat even more advanced.
Whoa.
Want to take a stab?
I mean, again, I don't know who would use these, but I think one of them is the exponential weighted moving average, EWMA as it's called. Again, it's used for continuous data, mainly for individual data points, sometimes with subgroups, most of the cases without. And here it is basically looking at your previous data point, and it's weighing or giving a certain percentage of weight to the previous data point. And then as you go further and further back into history, the weightage keeps lowering itself. And then you're comparing it on a run chart to see how is it trending over time. I think this is mainly used, from what I remember, to look at small changes, trends in a direction that you are trying to see if this is moving around or not. And Aaron, correct me where I'm wrong, because this is something that I haven't used. I've just theoretically seen it being used or talked about.
Yeah, and same here. And this is when you've really got your process really nailed down and optimized, and you're just measuring very small variation. It's not seeing all kinds of outliers or anything like that, or special cause, and you're just looking at minor fluctuations. This is when you would say, okay, we know there's some variation. We can employ this more advanced control chart to detect very tiny changes a little bit more earlier. So this really gives you an early indication if anything's going on.
Yeah.
Normally, most processes I've been in, this wouldn't be very helpful, because any small shift would be lost in the noise of a really out of control process.
It's either that, or I've never been blessed with processes that are so much in control.
Right, exactly.
All right. So the other type, or another version, similarly, is one known as QSUM chart, which is a cumulative sum chart. And this one you will have to explain, because I don't think I can explain this.
Yeah, it's basically the same thing, and it's actually difficult. I tried to go through it in many tabs. I want to let people know it's there, but I'm not going to say it's very intuitive. But it continues to sum up the values. Sums up the deviations of each sample of the value from the target value. So you have to set a target value, and then it looks to sum up the deviations from there. And once it hits a certain threshold, I think the threshold is, I'm looking at a zone chart. Once it hits a certain value, it's going to flag. But basically, it's still to detect small shifts from the target. for a process that's already very well in control. It's kind of like the EWMA, just another method of doing the same thing.
It's just a calculation slightly different, basically.
Exactly.
Yep. And then you already referenced the other kind, which is the zone chart, which is nothing but a crossbreed of the X bar R and the QSUM chart.
Yeah, right. And this one puts everything in terms of zones, and the zones are considered 1, 2, and 3 standard deviations from the center line, but they're only one rule here, and as it does this, whatever calculation, this one threw me off, whatever calculation it does, if once it hits above 8, it flags as a problem, and that's just the rule they put in place. I don't have any other rationale than that.
Got it.
And there are others, which I haven't had the opportunity to really get to know, but multivariate, so this is tracking multiple variables' impact on a control chart, and also a rare events chart, which would be something more like Black Swan or something like that. There's time between rare events kind of thing.
Interesting.
I will have to study that a little bit more, but for now, just say there's more.
All right.
All right, the meat and potatoes, like really getting into it. We talked about what it looks like. We talked about the types. They all kind of follow, I shouldn't say all, but many of them follow many of these same rules that are applied. And we have 8 Western Electric rules, starting with Rule 1. Jacob, this one's probably your favorite. Take it away.
Yeah, but before I go any further, wasn't there 9 rules?
Thanks for listening to episode 209 of the E6S Methods podcast. Stay tuned for episode 210 for Process Pulse Part 2, where we discuss the Western Electric rules. Don't forget to click like or dislike for this episode in the show notes. Tap click done. If you have a question, comment, or advice, leave a note in the comments section or contact us directly. Feel free to email me, Aaron, Aaron, at e6s-methods.com or on our website. We reply to all messages. If you heard something you like, then share us with a friend or leave a review. Didn't like what you heard? Join our LinkedIn group and tell us why. Don't forget you can find notes and graphics for all shows and more at www.e6s-methods.com. Journey through success. If you're not climbing up, you're falling down.